Okay. So I'm Dave, and this is population genetics and quantitative genetics. We are supposed to meet in this strange format, 2 hours on Tuesdays and 2 hours on Thursdays. And we're going to learn, hopefully, a whole lot of population and quantitative genetics during that time. As most of you have probably heard via, sort of rumors by your classmates, is this course is A, intended to be challenging, and B, intends to require / force you to become comfortable presenting in front of your peers. So the structure of the class is every week there will be an assignment of reading and an assignment of problems. And the problems are designed, or at least supposed to be designed, in a way to verify, or at least force you to really understand what you were supposed to be reading as deeply and thoroughly as we can. So the problems are often long, they're often challenging, and when class meets, the only thing we're going to do is go over problems. And the way in which we're going to go over problems is I'm going to have a randomized list of each of your names, and I am going to call on one of you. And when called upon, you will do the problem assigned to you. And you will never know what problem will be called on. So you will have to prepare the entire homework to be presented in class. And while for the last 10, 15 years when we've been doing this, it's been you just walk to the blackboard with your little sheet of paper and present the problem at the blackboard, from your feet. My suspicion is the vast majority of you will probably want to, will almost have to prepare something displayable via Zoom in order to do this. So all of the homework is in fact due to me the morning before class starts. So a natural thing would be when you finish your homework to make some electronic-y, PDF-y kind of copy of it, and be prepared to display your PD, to talk through, explain what you've done, and display what you've done for the problem. And that's going to be what class is for the next 10 weeks. Do we have any questions so far? The homework is likely to take you 10 hours a week, plus or minus a bit. Plan on that. Also, you are encouraged, I guess less so because of COVID, to work together as much as you can. Now that might mean nowadays working together online via some chat type situation, or meeting somewhere and sitting several feet apart from each other and wearing masks. But you are there. There is no such thing as cheating when it comes to homework. There is, did you do it and did you understand it? Or didn't you do it and did you not understand it? And if in order for you to figure out how to do it, you end up needing to have lengthy discussions with friends, you need to send me lots of emails and ask lots of questions, go right ahead. But in the end, you will be responsible for your own homework. So you will have to send me a copy of what you've done, and then you'll have to be able to present it in class. So how you got to the point of being able to do it and to understand it and to be ready to present it is not particularly important. But when class time starts, you should be ready to send me a copy and present it yourself. Any questions, anything? So in general, guys, it's more than okay to interrupt me at any time. You will not throw me off. You will not bother me. Just shout if you need to at any point. We're still okay? So let's see what we can, let me see if I can show you the syllabus and we can walk through it very, very quickly. Okay, share screen, syllabus. Are you guys seeing the syllabus?
Yes.
Yep.
Cool. So yeah, so this is the syllabus for the class. This is my name, my office phone. It's just my office phone number. Like, you're not going to get me there. Email me. For many, many years, Mike Swick and I team taught this class. Mike loves teaching this class, but Mike has become a very important person. He's like the associate major dean of the university right now. So Mike will probably not be around much, but if he has time, he may stop in to say hello. Don't be surprised if you see him. But most of the time, the dean is too important for this class. There is no teaching assistant this time, which means all questions about homework will come to me. And you should expect me to be doing all the grading for it. And so bug me if you got questions. You obviously all have the Zoom link because you're all here. That's very good. And we're supposed to be meeting Tuesdays and Thursdays. There is no maximum enrollment. That's bullshit. There is no permission requirement. Also bullshit. Okay, these are just some topics. So the way class is going to be graded is if you come to class and present your homework as asked, you will get 50% of the points. Full stop. Come, do your best, you will get 50% of the points. There are a midterm and there's a final. I don't really believe in grades in grad school in general. So if you come to class and do your homework and do your best, you'll get 50% of the points. If you take the exams, you're going to get a B. If you take the exams and do well, you're going to get an A. That's the class. The exams exist in order to encourage you to have done your homework and learn the material. If you do your very best, like you've tried all the homework, you've worked all the problems to your very best, you've come to class, you've presented to your very best, and you take the exams and you learned something, you're going to get a B. If you learned a lot, you're going to get an A. And so if you like A's, do learn the material really well. And if it turns out this is not for you, you do not like population genetics, this does not come easily, this is a slog, do your very best. Try all the problems, do your best on all the problems, come here in class. Explain why it went well, explain what you didn't understand. Explain, we'll talk through it and see if we can all understand it together. Take the exams, do your best, and take your B, and figure out what you really want to do with your life. That isn't this. Don't sweat grades, but do the work. The only way you'll get in any trouble in this class is if you demonstrate you didn't learn anything. And that probably means you didn't do a whole lot of the homework and you got effectively nothing right on the exams or close to nothing. The exams are designed in a way that if you learned nothing, you will get nothing right. They are challenging in ways similar and ways different than the homework. So there is no, you don't generally bullshit your way to points in the class. You've either understood it, in which case it's easy, or you didn't, in which case you're never, ever getting it right. So do your best. And if you've really tried, you'll get a B. Otherwise, and if you did good, you'll get an A. And
how are the exams structured?
And
Oh,
are they timed?
yeah. So traditionally, I hand the exams out at 10 a.m. on whatever day they're assigned, and you hand them in when you were done. And and they are supposed to take 2 hours, but again, I don't want to punish people because they like to work slower than others. They like to think harder than others. So traditionally, the 4 or 5 students who are working slower will come to me back to my office and continue working, at some table for another hour or 2 or 3 until they've finally gotten it done. So online, we're just going to try to do the same system, only you'll be on your honor not to have cheated. Um, the the issue is, of course, like so, right? Because I'm an arrogant shit, I like to pretend cheating doesn't help you on your exams. So I like to believe that if I've written a question, you'll either have understood it and gotten it right, or there is no amount of outside information that's going to help you with that problem. So you'll be asked not to consult with the internet and with books and stuff while taking the test. But honestly, I will not enforce that or try to enforce it because I don't think it's going to matter all that much. The tests are going to technically not be open book, but I will make no attempt to enforce that on you. What I will, though, enforce is when we take the exams in class, I don't make them open book, but I offer to allow you a sheet of paper to have written down every note, every formula, every idea on the single sheet of paper you want to have with you during the exam. So when we do the exams online, I'm going to ask you to send me a copy of that sheet of paper to make sure that you made one. And trust me, if you made one, you're not going to want to consult your books or your homework really at all anyway. So the act of going through your book and making that sheet of paper will probably be in going over your homework in your mind will probably be all the studying you want to do. So we're just going to pretend we're in class. We're going to pretend we're there. I'll give you the exam. You'll email it back to me when you're done. And hopefully you'll be done by noon. Maybe you'll be a little slower. You'll be done by 1 or 2 or 3, whatever. If you get done much after 2 or 3, I'll probably start, sending you emails saying, hurry up, hurry up. But that's about that. Other questions on that kind of stuff? So basic take-home message, you're going to take exams, you're going to present problems in class, but the goal is for you to learn as much as you can, do as well as you can. And if you do, you've got to move on if you didn't like it. And if you loved it, you'll get an A and you'll have learned you love population genetics and maybe it'll be part of your life. Career anyway. So there are 2 textbooks for class. One of them is Gillespie's book. Go buy that. It's not very expensive. You will need it. It's absolutely required, basically. The second book is Falconer and McKay's book on quantitative genetics. That is a great book. It's good to have in your collection. I would recommend buying it. There are several problems that will come from that book. But if you are a poor graduate student and can afford very little, buy Gillespie's book and figure out something else to do when you get a few problems from Falconer. Traditionally, this course has several reading days, but because of the truncation of the schedule, we will probably only have 2 this year, and it's possible those also will get cut. So here's the schedule for class. We are here now, meeting, saying hello. The next week, or not next week, Thursday of this week, in 2 days, nothing is yet due, but you have access, hopefully, to homework 1, which will be due next Tuesday. So at this time, Thursday, if you have questions on homework 1, I will be here to answer them. But other than that, what we're going to do is go through all of you and practice sharing screens, making sure everyone has the ability to share their screen, everyone has the ability to display a PDF or whatever they might want to display, or a PowerPoint or whatnot, and getting practice with all of you doing that sort of thing. I imagine many of you have already done it as part of one class or another, but I just want to make sure everyone can physically do that sort of thing. And the basic format of the class is homework will be due at 10 a.m. on Tuesday. We'll go over that homework all day Tuesday. We'll go over that homework all day Thursday. Repeat next week. So starting next Tuesday, we're doing homework 1 on Tuesday and Thursday. The week after that, homework 2 on Tuesday and Thursday, and so forth. It turns out I cannot be here March 2nd. That is a Tuesday. So we're just going to try to fit homework 5 into the Thursday session, although it may bleed over into the next Tuesday. We'll see. The first exam is scheduled for March 18th, and it will cover everything up until the Tuesday before the exam. And then we go back to homework 7 on the next Tuesday. I cannot be here also the week of April 20th. So there is no class scheduled for then. But after the week of April 20th, we have one more reading module and then the final exam. So you all may want to consider meeting during that time and prepping for exams together if you so choose, or not. Doesn't really matter to me. And hopefully everything will be done by April 29th. Does anyone have any important questions or comments on the schedule?
Hey, Professor, I have a question.
I'm sorry. Yeah.
Will you be holding formal office hours, or should we just reach out to you over email if you have questions?
Just reach out to me over email, Taylor, whenever. You know, even if this were regular, it would be like normal, where my door is either open because I'm accessible or I'm not, and just wander in whenever. And same thing with email. Just email me whenever. I will respond. If I am available at that particular moment, I'll respond to your email immediately. And if I'm not, I'll get to it as soon as I can.
Thank you.
And if we need to talk in person, we'll schedule a separate Zoom type thing. Other questions? Okay, so let me stop this share. Oh, there's stuff in the chat. Let's see. Oh, someone was kind enough to, oh, wow. There are scans of the books available?
No. So in my undergraduate career, I figured out how to find PDFs of textbooks. So I sent along both of them for this course.
Oh, that's wonderful. Cool. Excellent. Wait a minute, can I download them too? I'm sorry.
Yes, you can. They're downloadable from the chat.
That's very, very cool. Okay, guys. Well, you know, I would still recommend buying them because it's nice to have books on your shelves, but you are poor grad students. So you might want to wait till you're rich. That's very cool. So okay, I want to ask, this presumably is not maybe 100% legal, but okay. Anyway, excellent. Well done. Does anyone, this is great. Oh, I probably should take attendance now that people are all here. In principle, I will be taking attendance more or less every time just to verify you came and that you did, you know, and we'll know when you're called upon whether you came or not. So let me just make sure, and I've got most of your names here. So, but just to make sure. So Carmen is here. Is Linnea here? Somewhere in the chat. Linnea.
Yes, I'm here.
Yep, there you are. Okay. Is Marissa here?
Here.
Yes. Yep, there we go. And Sebastian, we just call it. You guys can scream.
Here.
Taylor is here. Kiana. Yes, I see it, Kiana. Mitchell was here, right?
Yep.
He got here early. Yeah. Yep. Christopher King. Is Christopher here? Yes. Uh, oh, Mega's here. Yeah. Do we have Mega here? No. That
Here,
is.
I'm here.
Oh, you're here. Great. Excellent. And is Michelle here?
I'm here.
And in Youngxian? Is that how it's pronounced?
Yes,
Oh.
it's Youngsan. I'm here.
Yep. And Jacoby?
Yep, I'm here.
Yep. And Jim Rose is somewhere. Yep. Brooke? Yeah, Brooke's been
morning.
responding to the chat. She's obviously here. And Julie?
I'm here.
Yep. Also, also joining us is Kevin, who you will see somewhere in the participant list. And is there anybody else I've missed? Okay. Before I give a little background lecture and probability, I was hoping to have all of you go around and briefly introduce yourself. Where are you in your career, and what you're interested in. Is that okay? If I don't have any major objections. So just do it in the order you appear in my participant list, which is close to alphabetical by first name. So Brooke, who are you and what are you doing? Where are you in your career?
Hi, good morning. I'm Brooke Talbot, and I am a first year in the PBEE program, so Population Biology, Ecology, and Evolution. And I am interested in applications of genomics to public health, specifically infectious diseases. Before I started school, I was an epidemiologist. Now I'm here in Atlanta in the middle of a pandemic, and it's great.
Yeah, well, it's the right place to be in a pandemic, I suppose, for an epidemiologist. Carmen.
Hi, I'm Carmen. I am also a first year in the PBEE program. I'm interested in pathogen evolution. And yeah,
Okay.
Yeah.
You've been around for a couple days. That's about what you got. Cool. Christopher King.
Yep. So I'm Chris. I am in the clinical psychology program. I'm actually first year, and I'm in Erwin Waldman's lab, looking to apply behavioral genetics to, studying externalizing behaviors generally. I spent a few years prior to this in education and have kind of made the transition over to psychology and genetics. So I'm looking forward to all of it.
Cool. Jacoby. Jacoby still here?
Yeah, yep, so here. Hi, everyone. My name's Jacoby Robinson. I'm a second year student in PBE, and I'm most interested in host-parasite interactions just generally, but I am right now pretty interested in how they co-evolve with each other, and so this will be a pretty useful class for me. So, yeah.
Cool. Jim Rose.
Yeah, hi, I'm Jim. I'm a second year in the genetics and molecular biology program. I joined the lab of Jerry Boss, which is an immunology lab, actually. But I have an interest in, kind of the population genetics, quant genetics stuff. So I'm excited to learn more about it. And we do stuff with B cells and T cells, so maybe there's something I can do eventually.
I think there's a little bit of there's occasionally a little bit of genetics in some of Jerry's work. Julie, you around?
Hi, my name is Julie. I'm a third year undergraduate student. I'm double majoring in applied math and stats and biology. I guess I'm interested in everything about pathogen evolution and math modeling, and also the PBE.
Excellent. So are you simply an overachieving undergraduate who plans to go to med school, or are you thinking about a science for a career?
I'm interested maybe being a biostatistician in the
Oh.
future.
Very good. Excellent. Hey, Kevin, welcome back.
Yeah, it's been a it's been a long road. So my name's Kevin. I'm currently actually not in like the academia circle. I'm a machine learning engineer in the startup world. I'm very interested in math, and I really like this course. Started taking it a long time ago with Dave, and I'm coming back to finish it up. And yeah, I did undergrad at Emory, and just interested in math, and I think the beautiful story that math can tell with biology. So here.
That's fabulous. Kiana.
Hi, I'm also first year clinical psychology graduate student in Dr. Waldman's lab, like Chris. My research and my interests largely revolve around mapping the downstream neurobiological correlates of genetic risk for mental illness, particularly disruptive, aggressive, antisocial behavior or externalizing behavior in youth. In a past life, I was primarily a cellular and molecular neurobiology researcher with primates, but I wanted to work a little bit more than peripherally related to humans. So I'm here for psychology now, and I'm excited for this course.
Excellent. Linnea.
I'm a third year and actually in the physics program, but my advisor works a lot with population genetics. I'm in Daniel Weissman's lab.
Yeah.
And I'm doing a lot of computer simulations of the evolution of cooperation.
Oh.
But like, I'm pretty interested in working with like real data, and I'm really hoping this class can kind of help me understand, grasp that better, I guess.
Yeah, hopefully. This isn't the most practical class for big data, but there'll be hopefully no aspect of the way in which you might analyze real data that you will not understand the fundamentals to right by the time the class is over, at least.
Okay, great.
but you're not going to learn, say, to run GATK or some of the big packages. But if you want to know, we'll talk about that. Anyway, that's the sort of thing we can get you up to speed on quickly if you understand all the basics.
Great.
Who's up next? If I'm not doing this wrong, Marissa?
Hi, my name is Marissa Duckett. I'm a first year in population biology, ecology, and evolution, PBEE. And I was a 2020 graduate in May. My degree was in microbiology. And now I'm kind of interested in biogeochemistry and pharmacology. So my current rotation is with Chris Sandra Quave and Jaap de Rood, and we're looking at microbes and butterflies.
Cool. Oh, by the way, everybody, I am unbelievably bad with names. I'm terrible at remembering names. I'm terrible at pronouncing names. And so when I butcher your name, understand that is a failing on my part, not a sign that I dislike you or I don't care about you or it's literally, I'm awful at it. And that I don't remember your name, despite us having talked for hours and hours in class. And sort of like when we bump into each other in the hallways and I can't remember your name, it is not you, it is me. And don't feel bad. I'm just really. So the canonical story is when I started grad school, I shared an office with 5 other guys. And every day before I walked in the office, I looked at the name, we had our names sort of written outside. I looked at the names on outside to try to make sure I remembered everybody's name in my own office. And I did that for like 4 months. So if I forget your name at any point, don't take that as a sign of anything other than Cutler's a moron, terrible at this. And if I continue to mispronounce your name, continue to correct me, and someday or other I will get it correct. And don't be embarrassed to correct me. And for God's sake, don't think the fact that I continually get it wrong is a sign that about how I feel about anything other than I'm just bad. Sorry. So I'm gonna so how do you pronounce your name exactly? Let me get it right, Mega. Is that it?
Mega, like Mayga.
Okay.
Medically. Okay, well, hi, I'm Mega. I'm actually a student from GT. I'm in the Biomedical Innovation and Development program, but I'm pre-med, so I'm planning on going to med school after that. And it was just pretty industry and like engineering heavy, so I was missing some science, bio, so I took this course as an elective.
Excellent. This course is still going to be a little, it's going to feel more mathy than biology, unfortunately. If you're really looking for a bio class, you've done screwed up. Sorry. Michelle.
Hey, I'm Michelle. I'm a second year in the PBEE program in Levi Moran's lab. And I study sex and why things reproduce sexually instead of asexually.
Cool. There's a chance, I think, we may leave that chapter out of the Gillespie book. That might be the only chapter we don't do. I don't think we currently are scheduled to do like Kondrashov's hatchet and stuff. But if you would like to do that stuff as a tutorial when the time comes, let me know.
Okay, thank you.
I think we leave out all the classical models of the evolution of sex because I don't think we've had a student here yet who was actually interested in the evolution of sex per se, and that is a whole field unto itself.
So that's the best possible field.
I'm not going to dispute why you think that. Okay. Is Mitchell around?
Hello, I'm Mitchell. I'm a first year in PBE as well. I'm interested in studying virulence evolution and parasite-host interactions and how that informs self-medication and on the host's part.
Oh, cool. And Sebastian.
Hi, I'm Sebastian Duran. I'm a biologist. I've been working with mosquitoes for a while, so I just play around with mosquitoes and figure out ways to either transform them or just kill them.
So you work on like introducing pathogens and stuff to them, or introducing transposable elements. Is that the idea?
Well, I've worked in the two main approaches using Wolbachia for controlling Aedes aegypti. So using the W. male strain in Colombia for population replacement, this strain causes viral blocking in Aedes aegypti, and it's able to block Zika, chikungunya, and dengue. And for my research proposal, for my PhD, I'm going to be working with incompatible insect technique, which is based on the cytoplasmic incompatibility caused by Wolbachia, and this approach is directed towards suppression. Cool. I'm just going to be playing around with mosquitoes.
Excellent. Taylor.
Hey everyone, nice to meet you all, by the way. I'm a third year in the biostats program, but my advisor is actually Dr. Mike Epstein in human genetics. And my primary research area of interest is statistical genetics with a focus on methods development.
And Shang-Chi. So close.
Hi everyone, I'm a third year in mathematics. I just want to say, Professor Cutler, you got my name correct.
Oh, excellent.
You don't have to worry about it. I guess that's what I tell everyone as well. So
whether or not it's true.
That's actually true. Whenever someone asks me, did I say it right? I said, yes, that's correct.
Good.
I mean, it just doesn't bother me anymore. So
yeah, you know, the answer is dumb Americans, move on, right? Nothing you can do about us. Don't bother. We're never going to learn. It'll be okay. So you're an undergraduate? Is that what you said?
oh no, I'm a third year in the math graduate program.
Oh, math graduate program. Oh, very good. Who's your advisor?
So who's my advisor? That's a good question. I don't know.
Oh.
So in math, I just want to say that everyone says, "Oh, I'm a first year or whatever," and you have an advisor and you're interested in blah blah blah. And it's like, this is so good. I mean, I wish what I know what I'm doing right now. I wish is that I can finish and graduate sooner than later. But yeah, in math it's a little different. I guess you have to take 2 years of classes and yeah.
So what sort of problems are you interested? What sort of what kind of mathematics makes you happy?
What kind of mathematics makes me happy?
Yeah.
I guess population genetics.
No. Seriously. What do you really like? Like, what is like? I mean, are you a topologist by like inclination, or you're an out?
No,
like what? No.
I'm in the applied math program.
Okay, so you're definitely applied. Okay.
Yeah. I was actually going to take your class 2 years ago, but your class schedule has like a weird time, so it's like 2 hours block, whereas every other class is 1 hour 15 minutes.
Right.
So there was a conflict, and I actually had to take my applied math class.
Sorry.
Yeah, I mean, yeah, that's okay, but
yeah. Okay. Well, cool. Excellent. I'm glad we've got a. So this class is, of course, sort of dominated by PBE students, which is it's a requirement for. And I'm glad we have a sort of fairly diverse group of students here. That it should make the class more fun with sort of differing. You'll find that many of these problems can be approached in multiple ways. And students with differing backgrounds will often approach them in very different ways. And it may make for a more fun class. Okay, do we have any questions about the structure of the class, about each other, about what's, how we're going to proceed, any of this sort of basic stuff before once we're done with this, I am going to launch into a remedial probability theory lecture. It is supposed to be prerequisite for everybody, and it is intended to more or less list ideas that should have been a prerequisite for you. And if those ideas if they do not seem familiar to you, the best thing for you to do between the next day or two or three is to strive hard to make sure the ideas are familiar, because they will come up over and over and over and over again over the course of the semester. So if this isn't stuff that is ingrained in you, this class is going to start getting nasty. But before we do that, any other procedural type questions?
Yeah, I had one question. So towards the end of the semester, when quals start picking up.
Welcome to the second years. Yeah.
Yeah. I wasn't sure if there was, I mean, like you said, it's going to be about 10 hours a week for homework, but
yes,
I'm imagining a situation now that might be kind of difficult towards around that time. So I didn't know if that would, if there would be any sort of leeway or anything like that.
The answer is we're adults. I want you to get as much as you. So here's the most horrifying pattern of this class ever. There are going to be a few students who are second year students who you will see as the strongest imaginable students in this class until, about February 15th. Well, most years will have been half done by February 15th. This year will be like 3 weeks in. And there'll be a handful of second year students who look like really, really great. And then they have to start turning in their qualifying exam paperwork. They have to start taking their qualifying exams. They have to start writing up proposals. And those students are you will see, do not contribute to class the same way they had before life went to shit for them. We are all adults here. We all recognize what's going on. We all know there's only so many hours in a week. And if you're taking your goddamn qualifying exam, your homework that week is going to suck. We're still going to go over it. If you want a few days afterwards to hand it in, maybe you will. Maybe you'll just hand it a piece of crap. So be it. This class is never, ever, ever designed to interfere with your career. It's designed to teach you something that hopefully will be useful for your career. But if there is something in your career that you cannot fail, like your qualifying exam, like your proposal turn-in, like you may not fail those things. And this class, and it turns out because you were doing that, your best in this class is awful. All right. And if it also turns out that the material for the class is important to your life, we can find a way to do it after the class is over too. You know, you can take your B for that semester, or maybe even incomplete for that semester, and then we can figure out how to do it after your qualifying exams are all over. This has happened every single year with every single second, that they're having a great time, or maybe sometimes a shitty time, but often they're having a great time. And then the qualifying exam stuff starts slamming them. And all you have to do is say, that's what's happened, and we'll figure out how to deal with it. Again, this is classes as graduate students exist to help you. The minute the class becomes sort of something that is causing your career to suffer, the class has failed. It is intended to be hard, intended to be a lot of work, because I think you will learn as much as possible by doing that. But if it is impossible to do the work because of your career, you will not do the work. And we'll figure stuff out. Okay. Don't, I think you understand. Basically try your best, and one fully understands that about immovable deadlines that may not be missed and you may not fail at, that you have to do well. And this class is not such a thing, despite its deadlines and whatever else. Other comments?
Can I also have a chance to introduce myself?
Oh, I missed you. I'm sorry.
So,
who did I miss? Who are you?
I'm Young-Song.
Oh, Young-Song. Sorry, Young-Song.
No worries.
Go right ahead. I'm sorry.
So hi all, my name is Young-Sun and I'm also a second year PBE student, but I think I haven't met some of first years in PBE students because I was taking a leave of absence last semester, but nice to meet you all, and then also nice to meet you all again.
Yeah, when I do idiot stuff like that, you can go ahead and interrupt me faster.
Nice.
Other questions? Did I miss anybody else? Okay. Actually, before I give this lecture, let's take a 2-minute break in case anyone needs to run to the bathroom and get a drink. And let us come back here by 10:50, and I will start a lecture on remedial probability theory.
Hi, I do actually have one question or oh no, is my mic not working?
Your mic's working.
Oh, good. I was just worried.
Sorry, I didn't know how to unmute myself in in screen sharing mode.
Sorry. Yeah, I know. I think there are ways that if you go into like view, you can set things interestingly. But I was kind of curious how, if there's ever been a struggle in finishing explaining the problems during the like 2 days that we have to explain all the problem sets, or if we should like have a estimate on how long it should take us to really go through a problem when we're explaining it.
So on average, there are between 10 and 20 problems. And on average, when you do them correctly, when you know what you're doing, they can be explained in 10 minutes if they are about the hardest problem I've ever given you, and about 3 to 4 minutes if they are an average problem.
Okay.
Sometimes a minute if they're graph. You shouldn't care about time in any way. Your goal should be to do the homework as well as you can, and then when called upon, to explain it as well as you can. And if class is going too slowly or we aren't making enough progress, I'll figure out what I want to do about that. You don't need to solve those problems for me. Let me figure out what I need to do to make class go quicker or slower. Your goal should be to learn how to present, sort of often somewhat easy, not elementary, but you should learn how to present work, mathematics, in a way that the rest of your colleagues can understand. And that should be your goal. And if it turns out it takes you a long time, great. And if it turns out it takes you a very short time, great. But your goal should be to figure out how do you communicate to these other 18 people effectively.
Fair enough.
Don't worry about it. Everything else is on me.
All right.
All right, it's about time. I'm going to assume most of you are back, and if you're not back, well, I guess you can't scream to me. Oh well. And if you've chosen to walk away from this part, I'm not offended. This is supposed to be remedial. So this class is going to be a challenge for me as much as it is for you guys, because I have taught this course since more or less since I was a grad student in the 90s, originally with chalk, then with sort of whiteboard pens. And I have never, ever created a lasting copy of anything I've ever done with this class. So, so despite the material being deeply, deeply familiar, the way in which we're doing the class will be a challenge, and we'll have to see how it goes. And there is a very, very good chance that if I systematically err, the way I'm going to systematically err is by going too fast. That if I get into a groove, I may start talking fast. I may start going through problems fast. And while at the blackboard, there is a limit to how fast I can do that, which is how fast I can write, which is sometimes pretty quick. But on here where it's already written, there's effectively no limit to how fast I could go. And my suspicion is that when I start really screwing up, the way I will be screwing up is by going way too fast. And It is in no sense a bad thing for you to scream, slow down, stop, what, why, huh? Why is that? That is never going to be a problem in this class. Just do it. And if you do it, there's about a 95% chance there were other students in class who weren't keeping up either, because I was not going at a reasonable pace. So don't be frightened. Don't be intimidated. Don't imagine you're going to hurt my feelings. Don't imagine you're going to throw me off or anything like that. Just, if I am not presenting material in a way you can understand and you think you should be understanding, tell me, and we'll figure something out. Okay? So, PowerPoint. So, random variables. What is a random variable? Random variable, here's what Wikipedia says. This was not a bad definition. A random variable is described as a variable whose value depends on the outcome of a random phenomenon. A random variable's possible values might represent the possible outcomes of a yet to be performed experiment, or the possible outcomes of a past experiment whose already existing value is uncertain or unknown. They may also conceptually represent either the results of an objectively random process, such as rolling a die, or the subjective randomness that results from the incomplete knowledge of a quantity. We'll often say something is random when it's actually knowable, but we just don't know it. The domain of a random variable, sometimes called a sample space, is defined as all the possible outcomes of a random variable. For example, when you flip a coin, there are two possible outcomes, a head or a tail. When you roll a six-sided die, there are six possible outcomes, the value at the top of the die. The term discrete, a discrete random variable, is one with a finite or countably infinite number of outcomes. I'm not going to define what countably infinite means, but it means largely that there is an algorithm under which you can count them. You can enumerate them. You can say that's the first, that's the second, that's the third, all the way up to infinity of them. A continuous random variable is one with an uncountably infinite number of possible outcomes. Boy, I got typos all over this. A continuous random variable is one with an uncountably infinite number of outcomes. So what is uncountably infinite? The number of real values between 0 and 1 is uncountably infinite. There is no algorithm under which you could count and say that's the first one, that's the second. All the real numbers on the line between 0 and 1 are uncountably infinite. In fact, all the numbers between 0 and epsilon, where epsilon is bigger than 0, are uncountably infinite. So most of what we'll do in class, like 98% of our problems, will involve discrete random variables. Probably maybe 2 to 5% will involve continuous random variables. All right, I got to remember how to move this easily. Okay, so let's imagine we've got some random variable x, and it is a discrete random variable, and there are n possible outcomes. So what do we mean by that? We mean there are literally, x can take on n possible things. It can be something, it can be something else, it can be something else, it can be something else, and there are n of these in total. And the things it could be, the values that x can take on, we'll call, in this example, x1, x2, x3, down to xn. So there are n possible things x could be, and those things are called x1, x2, x3, x4, and xn. And we imagine there is a discrete probability, which I'll call P1, which is the probability that our random variable x takes on value x1. P2 is the probability our random variable x is in state x2. P3 is the probability it's in state x3. Pn is the probability it's in state xn. And since this is a random variable, P1 plus P2 plus P3 all the way up to Pn have to sum to the number 1. That's what makes it a random variable. Technically, some of these P's could be 0, but there's some, none of them can be negative. They all have to be at least 0, and their sum has to add up to 1. Any questions so far? So the first thing we can talk about with our random variable is its expectation. The expectation of x, which we will write as big E of x, the expectation of x. That's how we're going to read this over and over and over again, the expectation of x. But we might very well call it other words. We might call it the first moment of x, or just the first moment, or the average, or the arithmetic mean of x, which maybe we even write often with a little bar over x, or just the mean, which maybe sometimes we'll write with a mu to mean mean, and maybe put a little x there to mean x's mean. All of those are the same thing, the expectation of the random variable x. And they're all defined as the probability of a possible outcome multiplied by the value of that outcome summed over all possible outcomes. So the expectation of x, which we might write as x bar or mu x, is equal to the probability x is found in outcome 1 times the value of outcome 1, which is x1. So the probability of outcome 1, p1, times x1, plus the probability it's in outcome 2 times x2, plus the probability it is in outcome 3 times x3, all the way up to the probability it is in outcome n times pn. And so that sum, p1x1 plus p2x2 plus da da da, that sum is the expectation of x. And we will often write that sort of notationally as this symbol here, which is a summation, the sum of pi times xi, where I can take on any value from 1 to n. So that is literally p1 x1 plus p2 x2 plus that summation is exactly equal to that series. And oops, what the hell? I didn't do that. Okay. If x had been a continuous random variable, and I have in here a sort of picture of a continuous random variable, where on this scale, on the sort of x-axis, I have the value of x, and on the y-axis, I have the probability density function of x, which we sort of think of as simply the probability of that value existing, or really that thing times dx is sort of the probability of it being in that state, x plus a little bit of epsilon. But in any case, the expectation of x is really just that for a continuous random variable is really just the same as a discrete random variable, where for a discrete random variable, we take the sum over all possible outcomes of the probability times x, where for a continuous random variable, we do the same. We take the sum of the probability of an outcome, which is really sort of p of x dx, times the value of that outcome, x, summed, or in this case, because it's continuous, integrated over all possible outcomes. And the simplest interpretation of a random variable is it's the arithmetic mean. It's the mean of the random variable, which is giving you a measure of where the center of the distribution is. For a continuous random variable, as like sort of drawn here, the mean is really sort of a picture of where the center of that is. Questions?
I have a question, maybe just about the definition for the outcome. So I was just thinking about, like, say if you wanted to talk about this in terms of just one dice or in terms of two dice. If you have like two dice, then you could have the same outcome twice or something like that. You kind of see where I'm getting at. I guess I was just curious, how do you define the outcome? Or
so I think we're probably actually going to do some problems like that. And I think the way we're going to approach them is we're going to think of one die as being a random variable. and we're going to think of the other die as being a random variable. And then we're going to talk about a third random variable that might be the sum of those two random variables.
Okay.
So we can talk about, you know, sort of the probability one of the die is in one state, the probability the other die is in the other state, and the probability their sum is equal to something.
Okay.
I think you're going to have some very specific questions that are formulated almost exactly like that. Other questions? The second moment of a random variable. The second moment of a random variable is simply defined as the expectation of x squared. And it's the probability of an outcome times the value of that outcome squared, summed over all outcomes. The first moment, the expectation of x is p1 times x1 plus p2 times x2, summed over all values. Boy, why does it keep doing that? Okay. This is a little smart computer that's guessing what I want. The second moment is equal to the probability times that value squared, plus the probability times that value squared, plus the probability times its value squared, summed over all values, which we can simply write as the sum of pi times xi squared. Or if this were a nice continuous variable, the integral of the probability times the value squared. I'm just introducing this concept because we're going to use it in a second. Do we have any questions? Well, actually, first we'll introduce even higher order moments, because you'll hear people say them. What is a higher order moment? A higher order moment is probably something beyond the second moment. It is the kth moment of a random variable, where k can be sort of any number, you know, so 3, 4, 5, whatever. And that's just defined as the expectation of x to the k. So the probability times x1 raised to the k plus the probability of x2 times x2 to the k, the probability of x3 times x3 to the k, summed over all possible values, which is just pi xi to the k. Or if this were a continuous random variable, it's the probability times xi to the k integrated over all possible values. Questions? And in fact, we can also talk about the expectation of any old function of a random variable, if the function is well defined in some fashion that I'm not going to get into. Questions? I'm sorry? So the function has to, you know, like be maybe differentiable continuously over the space or something, or only have a finite number of holes in it. But who cares what the definition is precisely? But for the vast majority of functions you will write down that don't involve sort of very weird shit, you can talk about the expectation of a function of a random variable, and that is the probability of the outcome times the function taken at the value of that outcome, summed over all outcomes. So the expectation of a function of x is just the probability of x1 times the function's value at x1 plus the probability of that it's in state x2 times the function's value at x2 times the times the probability it is in state n times the function's value at state n, which we can write as pi, the value of the function at xi summed over all states. Or if this is a continuous random variable, px fx dx over the sample space. Questions? So now we're going to look at a very specific function of a random variable. That specific function of a random variable has a name. That name is called the variance. And we will be doing stuff with variances of random variables for all semester long. So the variance of random variable x, or which we'll often write fx, or the variance of x, which we will sometimes call maybe the second central moment of x. Maybe if we're being really weird, we'll call it the square of the standard deviation of x, is defined as the expectation of a specific function. That function is x minus its expectation squared. And that's the probability of all possible outcomes multiplied by the difference between the outcome and the mean squared, summed over all possible outcomes. And the variance of x, we're going to think of as a measure of the width of the random variable. Maybe the width squared, depending on how you define width. But in some sense, it is measuring how fat and wide that distribution is. So the expectation of the variance is the expectation of x minus its expectation quantity squared. Oh shit, all my little 2's got in the wrong place. Sorry, these are all these 2's. Oh, screw me. All right, all these 2's are supposed to be exponents on this parentheses. It should read P1 times x1 minus the expectation of x, that quantity squared. P2, that quantity squared. Xn minus the expectation of x, that quantity squared, which we can write as a summation, Pi times xi minus the expectation squared. Or for a continuous random variable, that same thing over the integral space. Questions? All right, we started out with one random variable. Now let's get two random variables, x and y. We say x and y are bivariate random variables if whenever you observe a value for x, you also observe a value for y. So if you ever see a value of x, simultaneously you get a value of y. These are bivariate random variables. And we can think of sometimes you might observe an x1 with a y1 or an x2 with a y2 and so forth. Those should be n's there rather than 5s, another typo. But you can think of now all the outcomes here are all the possible combinations of x and y that you could observe. The value I've written here, x1 and y1, doesn't imply anything about them being similar in any way. And in fact, the way I've written it here, values of xi and yj might occur multiple times in this table. But this here is a list of all the different pairs of x and y you can observe. Neither the x's nor the y's, as written here, need to be unique. But the probability of all the potential outcomes, P1, P2, P3 down to Pn, n's, all of those probabilities still sum to 1. Questions?
Yeah, I have a question. This is Brooke.
Yep.
Are bivariates and the relationship between x and y here kind of similar to the idea of covariation?
I will be very explicit about that in a few slides.
Okay, great. Thanks.
I will be extraordinarily explicit about what the word covariation means and what it implies about the relationship between x and y. Okay. That, in fact, when we leave here, that should be one of the things you are most clear about, because we're going to be using that in the homework over and over again.
Awesome.
And if you're not clear by the end of the lecture, you'll be clear by the end of the homework because it'll happen. So,
can I also ask a follow-up question?
Yeah, Libby.
So say x had 1 and y had value 2 or something like that, and then you had the same outcome except that they flipped the values. Would those be two different outcomes, or would those be the same outcome?
Yep. Those are going to be two different things in the way of prediction. And a perhaps more usual way to denote bivariate random variables would be more of a table that listed unique values of x1 and unique values of x and unique values of y, so that you can think of now all the possible values of x and all the possible values of y. And what we have written in here is the probability of a particular combination. So we're going to write P11 as the probability that x takes on state x1 and y takes on state y1. And 1, 2 is the probability X takes on state X1 and Y takes on state Y2, and so forth. Many of these values might turn out to be 0. That's perfectly okay. It doesn't matter. But the sum over all these n times m values of P has to equal 1, and none of these can be negative in any way. This is probably a slightly more usual way you'll see bivariate random variables written. But the sum has to be 1. And of course, that means in the context of a continuous random variable, the double integral is equal to 1. Questions? So we can now talk about the moments of a bivariate random variable. First, we can talk about the moments of X, which is again, just the value of X times the probability summed over all possibilities. So the expectation of X is each of the individual probabilities times the value of X. So it's X1 times P11 plus X1 times P12 plus X1 times P13, all the way through X1 times P1M plus X2 times P21, all n by n terms. That's the expectation of X. The expectation of Y is the same thing, only you're using the values of Y rather than the values of X. We can talk about the variance of X, which is again, the probability times the value of X minus the expectation of X, which is just given up here. Quantity squared, summed over all possibilities. That's the variance. We can talk about the variance of Y, which is really just the same as the variance of X, only we use the values of Y and its mean, again, summed over all possibilities. Is this all making sense? Now we can define something called a covariance. And the covariance is defined as the expectation of X minus its mean times Y minus its mean. That's the definition of the covariance of X and Y. And the covariance is, again, just the probability of the observation, X minus its mean, stop that, Y minus its mean summed over all possibilities. And that is the definition of the covariance of X and Y. Do we have questions at this point?
I have a general question about covariance.
Yes.
So you described variance as being like the kind of the range of the myth of what that center of that distribution is. How would you describe covariance in that kind of simplistic term?
I'll tell you in a slide or two.
Yeah.
Other questions? So I'm going to first define a concept called independence. I'm going to say random variables X and Y are independent if all of these sort of statements are sort of true. That if the probability that X equals Xi and Y equals Yj, the probability of both those events happening, that's that probability Pij we defined in the previous picture. If Pij turns out to equal the probability X equals Xi times the probability Y equals Yj for all X's and J's. So X and Y are independent if the joint probability of Xi and Yj for all Y's and J's is equal to really the marginal probability of Xi times the marginal probability of Yj. So if the conjunction, both of them happening, is just equal to their independent chance of happening, we say they're independent. which is another way of saying that the probability that x equals xi, given that you knew, given, that's what this little symbol is going to be, given that you knew y was equal to yj, is just equal to the probability that x equals xi. So x and y are independent if the probability that x equals xi doesn't in any way depend on y's value, or vice versa. These are sort of the definitions of independence. If x and y are independent, then a consequence of their independence is the expectation of x times y equals the expectation of x times the expectation of y. If x and y are independent, then the expectation of x given y is just the expectation of x. If x and y are independent, then their covariance is 0. If x and y are independent, then their correlation is 0. So one interpretation of the covariance is that a covariance of 0, well, if x and y are independent, then necessarily the covariance is 0. So a non-zero covariance is going to be evidence that x and y are not independent. Now, it turns out it's not necessarily true that if x and y have 0 covariance, that they're independent. X and y can still be dependent on each other. This condition at the top might not be satisfied, even if their covariance is 0. But it's a pretty perverse situation when that happens. In most sort of physical, biological problem systems, if x and y are independent, their covariance is going to be 0. And vice versa. If the covariance is 0, there's strong evidence they're independent, or nearly so. But so the first interpretation of covariance is when it's 0, that means they're independent. All right, let's see some other interpretations. So I'm going to define 2 more words. One of them is a regression coefficient, or the line of regression, and the other is the correlation. So what I've done in these little sort of blue little dotties here is I have a random variable x and a random variable y. There are x on this axis, y on this axis, and I plotted a little blue point for every value xi, xj. Every value xi, xj is one little blue point somewhere on this picture. And then what I've done is I've found a line that passes through all of these points in such a way that the distance between each blue point and the line in this dimension, along the sort of y dimension, this distance in this direction, that distance squared is as small as it can possibly get. So I want to find a line. I found a line that minimizes all of these distances squared. That line has a slope. The slope of that line, which we'll often call the slope of the regression line, I'm going to call this the regression line. I'm not going to tell you why I call it the regression line until maybe week 8 or 9 in the class. But in week 8 or 9 in the class, you will fully understand why this is called the regression line. But this line that minimizes that distance, which we'll call the regression line, you can prove, I didn't bother, but it's not very hard to prove, that the slope of this line has value, the slope of the line is given by the covariance between x and y divided by the variance of x. That's the slope of this line. So the natural way of now thinking about the covariance is if x and y are independent of one another, the covariance is 0, which means the slope of the line that best fits these points is just flat. On the other hand, if the covariance between x and y is positive, that means the slope goes in this direction. Because of course, So, oh, I didn't actually say it, but a dumb fact about the variance is it's defined as a value minus the mean squared, summed over times a positive or at least non-negative number. That sum has to be positive. There's no way for a variance to ever be negative. So the slope here is, we have here a non-negative variance. So the slope of this line is the sign of the covariance. If the covariance is positive, the best fitting line is positive. And if the covariance is negative, the best fitting line goes in that direction. And the covariance here is giving you a sort of a picture, particularly when it's scaled to the variance of what the line that sort of best fits these points looks like. And you can actually think of a few lines that best fit these points. The regression line is the one that minimizes the distance in the y dimension. You could also imagine minimizing the distance to the line in the perpendicular dimension, in the sort of way that minimizes the sort of max that makes the line as close as possible in any old orientation. The line that minimizes the perpendicular distance is called the correlation. And we can also prove relatively easily that the correlation between x and y is just the covariance divided by the two variances square rooted. So correlation, I should probably put this on the slide too, has the neat feature that it is always between -1 and 1. So a correlation is sort of very well scaled. Again, a correlation of 0 means the best fitting line is flat. There's really no relationship. They are independent of one another. A correlation of 1 says they're sort of perfectly on the line with one another, and the line is positive. A correlation of -1, they're perfectly correlated with one another, and the line goes that way around. So their signs are kind of reversed. But correlation is nicely scaled between -1 and 1. So we can also talk about linear functions of expectations. So x and y are bivariate random variables. Let a and b just be some numbers. They are scalars. They are fixed numbers of known quantity. They're not random in any way. We can prove very easily that the expectation of some number a times x is just equal to a times the expectation of x. The expectation of x plus some number b is just equal to the expectation of x plus b. Therefore, it will come as no shock that the expectation of a times x plus b is equal to a times the expectation of x plus b. The variance of a times x is the variance of x times a squared. When you take a random variable and multiply it by some number, the variance changes by that thing squared. We're going to use this over and over again. Taking a random variable and making a linear transformation translates the mean, sort of moves the mean, and it multiplies the mean by that same value, but it has a squared effect on the variance. So a times a random variable has variance a squared times the variance of the original variable. If you add a number to a random variable, though, it doesn't change the variance at all. Taking a random variable and adding something moves the mean, but leaves the variance the way it was. Doesn't change how fat that random variable was. So if you do a full-on linear function of the random variable, ax plus b, the variance is changed by a squared, but that b had no effect on it. Now let's look at combinations of random variables. We have random variable x, random variable y. No matter how they're related to each other, the expectation of x plus y is equal to the expectation of x plus the expectation of y. You can always pull these things apart and simplify them into the expectation of, oh, what on earth? So you can always pull these apart and simplify them into the expectation of X plus the expectation of Y. Variances aren't quite so simple. You take the variance of a random variable X and add it to the random variable Y, you're going to get something with variance equal to the variance of X plus the variance of Y plus twice the covariance between X and Y. If you tried to take the expectation of something that wasn't a random variable, it's just the number A, it's always A. Its expectation is A. The variance of the number A is 0. There is no variability around a number that is A. If A is just a number, it is on average itself, but it has no variability. And if you have your two random variables, X and Y, the expectation of X can be thought of as the expectation of X, given that you know what Y is, the expectation of that quantity. So summed over all possible values of Y times their probability. And the variance of X can be written as the variance of X given Y, the expectation of that quantity, plus the variance of the mean of X given Y. And we'll use those sometimes, particularly at the very end of the course. And I think that's all I was going to tell you. So, any questions?
So will this class just be like all probability, or is this an introduction just so that we have the tools to do something else with it later on?
This is
I'm not exactly sure what. Okay.
The first week will be all probability. Everything after this is straight population genetics.
Okay.
So this week we will practice with these tools. Next week, or rather, starting on Tuesday and Thursday of next week, we'll be practicing with these tools. The week after that, we'll be using these tools to learn everything there is about Hardy-Weinberg equilibrium. The week after that, we'll be learning everything we can about genetic drift. The week after that, 2 weeks after that, we'll be about selection and so forth. But the way in which we are going to think about Hardy-Weinberg equilibrium, genetic drift, natural selection, mutation selection, but the way we're going to think about all the concepts in population genetics, we'll be using these basic tools. So this week, we're going to practice using these tools until they become second nature, so that when we have to use them to understand population genetics concepts, we won't be fighting the tools. We'll be sort of using them to get grasps on sort of fundamental questions of genetics and population genetics. Does that make sense?
Yes, thank you.
Other questions?
Hi, Dr. Cole. I have another question. There's quite a bit in Appendix B about stochastic processes, and I was just wondering if we were going to get into that in this course.
A little bit. We're going to use a few results here and there from it. I will probably not, well, you'll see. That's the best I can say. You'll see. There's probably going to be less than you'd want, Taylor. But if you want more, we can talk about it.
Thank you.
Okay, so that's all I got. And this will also be a feature of the class. When we're done, we're done. There's literally no point in being here if there's nothing more to say. So on Thursday, we're going to come back here and we're going to make sure everyone is capable of sharing their screens. And I would recommend you download homework 1 and give it a try. And if you run into problems or questions about it, we will discuss those problems or questions. And it's very possible Thursday will be a very short class. On Tuesday of next week, I will have a randomized list of your names. The person at the top of the list is going to be problem 1 until we get through to the last problem in homework 1. And then we're going to repeat until we're done with the PopGen book. And it's quantitative genetics and some other fun stuff. Questions? All right. See you guys Thursday at 10.
Thank you.
Thank you.